In the previous session, we have covered a topic called synthesis. Synthesis is nothing but process of converting your RTL code to gate level netlist. That means you are translating RTL, Verilog code to gate level netlist, mapping to a technology library, and optimizing your design. So these three steps covers synthesis. So using cadence genus. So my audio is clear, right? Everyone. Everyone is able to hear me. Kasi, Tarak, yes. So there are very less participants today. Okay, done again. After as the digital asset design flow, as a part of digital asset design flow, okay, the first step was specifications, RTL design, RTL verification, and once successfully the RTL is verified, okay, the physical design or the backend part, we call it as synthesis. The first step. Synthesis is the process of converting your RTL code to gate level netlist, mapping to a technology library with some optimization based on the user constraints and design constraints. So what are the inputs we are providing for synthesis? We are providing Verilog netlist. Okay. And next is .hdc, that is constraints file. And next is technology files, which are libraries. And we are asking the tool to syngeneric, synmap, and synoptimize. Syngeneric will do synthesis generic way in such a way that it will convert your Verilog English to gate level netlist. And synmap will do the mapping of the logic gates to the technology library cells. And optimization based on the logic. If you want to reduce the number of gates, reduce the number of logics, then synthesis optimization step will be given. Once after these three steps are done, okay, we will check the reports of area, timing, and power. So how we are going to calculate the area of synthesis? Okay, from the reports of synthesis area, we will have the report. Okay, only the gate area we will be having. Suppose consider my design has 1000 gates. Each gate size is of 1 square mm. Then what size I need my chip size? 1000 square mm. So at the time of synthesis, we don't have the clear dimensions of area of the chip completely. We need to estimate or we need to understand. How we are going to estimate the area of the chip? By calculating the area of gates. So these many gates are there. Okay. So we want to place all these gates in the synthesis after floor plan, in the stage of floor plan in physical design. Okay. For that, I need to assume the gate area and some buffer space for routing, clock synthesis, and some engineering change order ECU. So whatever I'm speaking, the terminology is important in VLSI. Okay. And after estimating the area from the gate count, next is power. The power is nothing but we don't have the actual power. This is also based on the report analysis generated by synthesis tool. So it will generate the area, power, how much power it has to consume. Rajreddy, voice is not clear or it's not audible. Is it now audible? Kriti, you are clear. Tarak, you are clear. Rajreddy, still you are not clear. So try to rejoin the meeting. Okay, Rajreddy. Others are visible. Jaydeep, yesterday or day before yesterday only, I told that I am having severe throat infection. Still, I am struggling to take the classes. Okay, I'll try to raise the voice. Okay, Jaydeep, thank you. It's okay, it doesn't matter. If you are not audible, you should say that. If you are simply sitting idle in the class, whether you are following or not, I should understand that. Okay. Rajareddy, are you able to hear me now? For today's presentation, I will be showing it up on the screen. It is taking longer time for my folders to open. Okay. So because there is lot amount of data. So that only I am trying to recap it for 5 minutes in the past session what we have done. And based on the synthesis, mapping, synthesis, optimization, and in the last step, we are going to generate the reports for area, timing, and power. And the timing power, power report, what we got in the synthesis stage is not the final power report. Okay, it is based on the gate area, gate powers, and virtual routing or virtual clock nets power. So we don't have everything on the physical part. Everything is on the virtual part. So once it is placed physically, then only we can estimate completely what is the design area, what is the design power, and what is the design timing analysis or frequency. So the timing also, there are two types of timing calculations, that is setup time and hold time. So the timing concept is called static timing analysis. Whether you do setup timing analysis or hold timing analysis. Whatever the timing analysis might be, the timing analysis is called static timing analysis. And whereas coming to the analog circuit design engineers, whatever the timing analysis they are doing is manual timing analysis, that is dynamic timing analysis. They does this timing analysis based on the circuit. And here we have the circuit based on our synthesis netlist. Clear everyone so far? Now we are going to, sir, why power area reports after synthesis are not accurate? Bhuvaneshwari. So synthesis is a process of converting your RTL English to gate level netlist. And you don't have the complete chip area. You are not placing your standard cells. You are not placing your macros. You are not doing complete clock tree synthesis. You are not doing your signal nets routing. Then how can you estimate the power? Then how can you estimate area? And how do you get the actual timing analysis? Once you place them only, you will be getting the correct reports, correct area, correct power, and correct timing analysis. Unless until you place them physically on the size of the chip, you don't have anything calculated accurately. You need to assume or you need to estimate. That is how we follow in synthesis. Here so far? Any questions on the synthesis part for another 2 minutes? So whatever I'm teaching in the class, everything is available in the Google. Try to check this concept and try to prepare your own notes. And if you are very much interested, you opt for your MTech in VLSI. Okay, then you will be getting a job definitely in VLSI industry. If you are going with your BTech and if you want to learn these things, try to learn in some coaching centers. Okay. This internship course will give you the index of your VLSI career. This is only the index. This is not completely. So unless until you make your hands dirty or you practice the designs or you code the some design, you make your tools access, then only you can become a VLSI engineer. Is everyone understanding my words? Okay, sir. But after I learned PDFs, but it was not open. Means, Raj Reddy, can you please tell me a little more clear? I didn't understand your wordings. Yeah, Raj Reddy. Sir, classes after whatever the notes or whatever the PPT we are giving are not opening. Okay. I'll ask my team or you can request the Blackbucks team. You send a screenshot, this PDF is not opening. They will try to reply you or they'll convert the PDF to Word or PPT and they'll send it back. Okay, Raj Reddy. Is there any portal or any Telegram group is there? I think you just ask the Blackbox engineers to revert on your message that I'm unable to open the PDF. They'll help you out. Right. Any more questions related to technical part of synthesis or physical design or asset design flow? Next 1 more minute. While generating bit stream, sometimes dot bit file doesn't generate automatically, sir. How do how to find the path of dot bit file? Janavi, which tool are you using? Janavi, Xilinx Luado, sir. So how we are generating the bit stream? Even I am very less used to Xilinx Luado. Uh, so first what you need to do is you need to create a project. You need to create a design file based on the mapping to a FPGA board. Intex, Vertex, RTX, something board will be there. So to that, you need to create a mapping file. Okay, that mapping file is called Verilog file. And you need to write your Verilog code. And if you right click that and create a new file, then it will create a test bench file. And the bitstream file is mainly used to download the data to the FPGA board. Unless until if you are doing software simulations, you don't require bitstream file. If you want to do hardware simulations, okay, on the FPGA board, then you require bitstream file. Janavi, is it this clear? Janavi, you are able to listen me? Clear, sir. Yeah. So today's session we will be covering about Jaydeep, yes, yes. Whatever the internship training, whatever I am giving, okay, this is completely related to the cadence tools. So for Verilog and RTL synthesis, RTL verification and RTL design, we were using cadence Xcelium tool. Okay. So next is for synthesis, we are using cadence genus tool. And for physical design, like placement, clock tree synthesis, floor plan, routing, all these steps we are using Novus. Okay. And apart from this, I will be showing you one more tool also, that is conformal logical equivalence checking. So at each and every step, whether my design is working correctly or not, to check the correctness of my design, I need to go for formal way. Okay. So whatever you are doing before synthesis is functional verification. And after synthesis, whatever you are doing, that is formal verification. Each and every flow of VLSI steps has its own job roles in the industry platform. Clear, Jaydeep? Here, Jaydeep, please reply whether you got my point or not. Sir, cadence virtues or where it is used. This is used for analog circuit design. So after completing the digital part, we will enter into the analog part. Okay, Jaydeep. So I'll teach you the cadence virtues also. So designing some circuit and how we do the simulation and how we write the test bench and how we generate layout. The lengthiest part is digital and the simplest part is analog. And based on the knowledge, the complex part is analog and the simplest part is digital. Okay. The more tools, the less complexity of design, and less tools and more complexity of the design is analog. Okay. So analog circuit engineers, they are very uh, good in analog subjects like transistors, MOSFETs, circuit design analysis, theorems, and all these concepts. Network theorems, electronic circuit analysis, all these subjects you need to be very much clear and thorough. Okay. So I'm trying to open my PPT for the day, but my laptop is responding very slow. So give me please allow me another 2 minutes to open the PPT. Okay. Yeah, Bhuvaneshwari. I am taking 2 minutes of time to open my slide presentation for the day. Is it okay? The laptop is stuck. Sir, take your own time. No. Tarak, this is our class time. So if you have any questions, please ask me. Related to subject. So you are able to see my screen, right? PPT is not yet open. Right. Sir, what is the abstract view names and layout on physical library? So there are two types of views. Okay. So this you can see mainly in analog circuit design layout part. Okay. So we will be seeing once after the circuit design, we will be trying to generate the layout. Layout is nothing but converting your circuit to stick diagrams. So that is called layout. So that layout part can be abstract views and layout views. So abstract view means it will be visible only the base metal layers. The base metal layers like poly, okay, oxide, and these layers. And metal one, metal two, sometimes. Okay, not all the times. But whereas layout, so till top metal layers. So if you are using some 9 metal layer design, some base layers, poly oxide, and metal one to metal 9. All the metal layers are visible in the layout. Okay. So this is what related to the physical libraries. The physical libraries are called as PDKs, process design kits. Tarak, you are trying to explore Good. Yes. Still one more folder has to open. So the next step of physical design is floor plan. Floor plan is nothing but what is floor plan? I have explained. Someone can type in the chat. What is floor plan in physical design? This is immediate step after synthesis. RTL design, RTL verification, synthesis, floor plan, placement, clock synthesis, CTS, routing, sign off checks, and chip design. This is our physical design flow or ASIC digital design flow. Yes, exactly. Gupta. We are going to declare the die area and core area of my chip. So as per the report of synthesis, okay. So in synthesis, we will be getting the area of standard cells. Using that area of standard cells, we are going to estimate how much area we should use for the chip design. And this is also completely on a trial and error basis. So initially what we will do, based on the 50% or 60% utilization, okay, for placing standard cells and for placing macros, we will be deciding the die area and core area. Okay, so how we are going to do the house construction? So we have a 200 square yards of plot. Okay, so we need to do a floor plan. How many rooms we need, how many washrooms we need, how many puja rooms we need, and all these things we are going to decide based on the square yards. And what should be my kitchen size? What should be my master bedroom size? What should be my children bedroom size? And what should be my hall size? What should be my washroom size? Based on this all sizes, okay, or the dimension of my rooms, I am going to split my 200 square yards of plot into a floor plan. And that floor plan includes my compound wall and my house room walls. Compound wall to room walls is offset area. That offset we call it as IO ring area, input output pads. Apart from die area and core area, whatever we are going to declare in floor plan. Gupta, you are right, Rohit. Thanks for your answer. Still any more answers? What all? See, yeah, IO ports. For each and every step in physical design, we have inputs, process, and outputs. The process is nothing but we are going to do whatever the steps we are performing in that stage. And we are giving some input files. What are those input files? And we are getting some output files. What are those output files? Bhuvaneshwari, very good answer. Combinedly together core area plus IO area is that is die area. Die is the outer part of my chip. From die to IO ring, we are going to do packaging. Packaging is nothing but the black color part of my chip connected with the silver pins, where we see in our lab any 555 timer or op-amp 741. Correct? Everyone has done these experiments in your labs, practicals. Ishwar, yes, good. You have done op-amp 741. Ishwar, what experiments you have done using IC lab? Can someone tell me using IC lab or circuit analysis lab, what experiments you have done in your academics? IC 741 Sharan Reddy, already I told you. Okay, that is 741. Please tell me one experiment name using IC 741. Sharan, IC 741 is the correct answer. Okay, that is an op-amp. ADC conversion, Jansi, Srijan. Comparing amplitudes, sir. Correct, correct. Bhavani, adders, subtractors, IC 4004. Charan, what is IC 4004, 4005? What are those IC usages? Yeah, Jansi integrator differentiator using 741. Logic gates, sir. So what logic gates? 4004, 4005. Bhuvaneshwari oscillator, correct. Any 555 timer. Multivibrators, correct. Astable, monostable. Yeah, main bridge oscillator. DAC. Bhavani, what is DAC IC number? And NOR gate, Sharon, thank you. I forgot those IC numbers also. It's long back. Differential amplifier, Sadik, very good answer. Using 741 IC. And the most important one is differential amplifier comparator. We are going to design using 741 op-amp. Yeah, Pavan. Correct. Differential amplifier is the correct answer. Using 741 IC, we have designed differential amplifier. Okay. So square wave generator, what is that? IC? I don't know the IC name. Square wave generator. Any 555 timer, I think. Everyone able to see my PDF? Input files for and floor plan. My screen is visible. Input files and floor plan. Audio is clear? Someone please confirm. Bhavani, yes, thank you. So, as you all are intelligent and very attentive to my sessions, okay, this is my chip. Okay, so floor plan is nothing but we are going to design a chip which has die area. This is die area. This is core area. Okay. So this is how we design the floor plan. This is my complete 200 square yards of plot. Okay. This is my compound wall and this is my rooms inside walls. And the house surrounding, I have a compound wall. That is core area. And inside house, I have a placement of my master bedroom, puja room, kitchen room, and other dining area, all these things. So I need to do the floor plan like this. And this is my utility. And this is my hall. This is my kitchen. This is my master bedroom. This is my washroom. This is my utility. And here is my parking. And here is my gate. Okay. This is how we arrange our house based on the given plot size. Similarly, we use the chip dimensions also to do the floor plan. Okay. Is everyone able to follow me? Understand what is floor plan? So, understanding about the topic floor plan, input files list, understanding of each input file, what is block level design, creating core area, die area, parameters, port placement, macros placement, and macros, what are macros, and power planning. In floor planning, we have an instantiation of topic called power planning also. For each and every chip to function, for each and every transistor, for each and every logic gate, to make it work, we need power. So we are doing power plan. Clear? Everyone, the contents. Any question on the contents? Input files for load plan. Understanding each input file. What is block level design? Creating core die and die area and its parameters. Ports placement. What are macros and what is macros placement? How we are going to place them? And next is power planning. Clear so far? Everyone understood what we are going to learn in the floor plan stage? Someone please reply yes or no. If yes, we'll proceed further. If you have any questions, we'll take up the questions. Tarak, yes, sir. Thank you. Tarak is the number one person who replies very quickly. Hemant, thank you. Keshava. Keshava. Okay. So many. Devi. This one. Yes. So in physical design, these are the input files which we are going to give it to the floor plan tool. If it is from Cadence, we are going to use InnovoStream. Here not do. Okay. So next is the input files. What are the input files we are using? SDF, SDC, standard design constraints. Next is UPF, Unified Power Format. These all are the terminologies. Next is CalDEF. Def is nothing but scan is scan. Def is nothing but design, exchange, format. These are like DB files, database files. Next is def. Next is libs. Libs are related to timing. Tech files, which are related to metals. How many metal layer design you are using? Correct. We will learn. Okay, one step by step. First, we are understanding the input files required for floor plan. Correct. You are with me. We should not learn all together at a time in a one day full syllabus of MTech. Okay, just we will learn today floor plan. Yesterday we have learned synthesis. From synthesis, we are getting some files. That some files we are giving as an input to floor plan. Okay, so what are the files? Files generated as the output from synthesis. We got standard constraint file. Next is unified power format file. And scan-def is nothing but while doing the DFT, okay, as we have told, if some logic in the chip is not working, we are using the scan cells to scan the design. So that scan-def file will be given by DFT. That is also from library. So we will insert that scan cells in our design. Next is design exchange format. If we have some macros, that is soft macro or hard macro, that macro is already completely designed. That logic we want to use in our design. So we will take it as a def file format. Def is nothing but design exchange format. It can be designed in Cadence, it can be designed in Synopsys, or it can be designed in any other tool also. Rohit, design for testability is nothing but, yeah, Bhuvneshwari, I'll explain you. Let me complete the explanation for Rohit. So I have a chipper. So this logic is not working properly, but I have scan cells inserted at my placement stage or floor plan stage. Using these scan cells, I need to debug where this logic is getting defective. I'll pass some test vectors using ATPG, automatic test pattern generation. These are some techniques. Or scan boundary. Using these techniques, we'll pass test vectors to my scan cells. Using these scan cells will try to understand what is the logic or where is the defect in our particular block of my chip. If that is understandable by the designer, okay, he can rectify the design before tape out. If after tape out, if it is not working, then we have to go for a redesign. We need to wait another for project time. So to avoid that disturbance or lack of time, or we need to make a precaution that this design, each and every block is working physically. For that reason, we are using the concept called DF. And there is also another concept, DFM, design for manufacturability. If design for manufacturability is checked after physical verification. So DFM will be done based on the layout part, on the stick diagrams. Okay. Did I answer your question, Rohit? You are clear? If you have any doubt, please let me know. Okay, sir. Next, Bhuvneshwari. Sir, does scan-def file do verification in chip? No. Scan-def file is nothing but it has some libraries which are related to scan cells. See, we have .lib files. .lib files has Verilog model files and it is related to the standard cell libraries. Similarly, scan-def file has standard cells with scan pin. While I am explaining the DFT, okay, so DFT cells, suppose consider D flip-flop, okay. D flip-flop has inputs D, Q, clock, sorry. Q as the output and reset, preset, and another pin called scan. So based on the scan pins, scan connection, so these all scan connections are given to the VTP. So that this D flip-flop where it is connected in the logic using scan cell, then we can try to get the information where we are going to use the logic in our design block. So these logical cells are not available directly in our design library. They are from scan. That is given by Foundry. Okay. Bhuneshwari, is my explanation clear? Yes. So Hemant, scan-def and def. Scan-def is nothing but which is related to the scan cells. Def file is related to the previously we have hard macros or soft macros. Okay. This is some other block of design. That design we want to reuse in my design. So that kind of designs we get in the form of def file. So I have a processor or system on chip. I want to build a system on chip. Okay, which has 4 blocks: CPU, RAM, SPI, and ROM. Okay, so already CPU is available, SPI is available, ROM is available. Designed freshly. Okay, but I want to reuse my RAM. So from the previous design, I want to get the RAM of same file. So I want to reuse. This file is saved as def. Design exchange format. Is it clear, Hemant? And each and every step of our design, we can save our design files as def format, which are database file formats, where we can import or export or reuse these files in cross-platform tools from Cadence to Mentor Graphics to Synopsys, or any other cross-platform tools. So only they are called as design exchange format files. Clear so far, everyone? The input files. What are the input files we are using for floor plan? SDC, UPF, Unified Power Format, ScanDef, def files, library files, and technology library files. Technology library files as the metal information and metal thickness, metal density, and all these things. And their timing, delays, and everything are available in libraries. .libs. Clear, everyone? So far? Should we proceed further? Yes or no? Any question? Please reply someone. Okay, sir. I think many of them are sleeping in class. They have left it running, and they are doing the end of work. Okay. So coming to the input list, the input list consists of technology file, TLP file. TLP is nothing but technology lookup tables. Next is library exchange format, .left files. Next is liberty timing file dot labor. Next is gate level netlist dot v file. Next is standard design constraints or synopsis design constraints dot sdc. These all are the input files. We are going to give it at the stage of floor plan. So these files, TLUP files, table lookup files, we are going to give it in synopsis. This is used for synopsis. Whereas for cadence, we will be giving the input as left files. Okay, layout Excel format or library Excel. So technology file is nothing but .tf file, which has the technology information like 90 nanometer, 45 nanometer, 10 nanometer, 5 nanometer, 7 nanometer. Table lookup files has the gates delays like maximum time delays, minimum time delays, maximum power, minimum power, maximum areas of the gates, minimum areas of the gates. So whatever the standard cell library will use in our .lib files, okay, each and every cell has maximum area, maximum power, maximum timing delay, and minimum area, minimum power, minimum timing delay. And there are also some files which has moderate area, moderate power, and moderate timing. So whichever the files we need to use, we will select it from TLUP files. In case of synopsis. In case of cadence, we will use .lib files. And the technology file .tf file is in synopsis and .lib file is in cadence. .lib file is also in cadence. .v is common and .sdc is also common. Here the name is synopsis design constraints. If it is goes for synopsis tools, if it goes for the other tools, it is called standard design constraints. Clear? The inputs list. Yes, sir. So clearly explaining the technology file. So what technology file information has? Manufacturing grid definition, and site unit tile definition. Grid means, so when we declare the floor plan, we have horizontal lines, vertical lines. Those are called follow pin lines. Those follow pin lines are called as, they are made to form a grid where our standard cells are fit into these follow pin lines, height and width. Like this, we have some horizontal lines, vertical lines. So these lines are called as follow pin lines. So we place the standard cells in between this. This will fit the height and width of our follow pin lines. So these lines forms grid. Okay. So technology file will have the grid information. And next is name number conventions for layers and layers. So these are metal layers. This is metal 1, metal 2, and metal 3. So all the metal layers are of different colors. Blue, okay, red, and violet. This is some 3 metal layer deal. Okay. So there is orange color pillars. These are called vias. Vias means we are connecting metal 1 to metal 2. This is connectivity based on 3 vias. As the width and length of the metal 1 is very high. It is almost on 1 centimeter or 1 inch. So only to make the connectivity clear, we are using 3 vias. Whereas coming to metal 2 and metal 3, we have 1 via. Why? Because these are of less width and less size. This is how we are going to do in the physical design. And physical electrical characteristics of the layers and wires. Physical electrical characteristics. Physical means dimensions, length, width, and thickness of each and every metal. And electrical characteristics means resistance, capacitance, inductance, and any losses in the metals. Those all are electrical characteristics. These properties are written in the file called doc technology. In physical characteristics, what we will have? We will have minimum width, minimum spacing, pitch of layer as present. Minimum width. What should be the metal width? Minimum spacing. If we are drawing a metal, another metal here, okay, to this metal, we should have minimum spacing. If you don't have minimum spacing, the charge flowing in this metal, will dominate. So there will be a violation that will cause crosstalk. So this is the live example. Whenever a passenger train going beside a Shatabdi or a Rajdhani Express, okay, how do you feel? The force of the air, if you are standing in the door or if you are seeing it from window, okay, there should be a minimum spacing between rail to rail if the trains are traveling. Else, there is lot of air friction, air collision, and other things. So to avoid this air friction, air collision, or any damage to the infrastructure, we are putting rail to rail defense. Hope everyone is clear with this. Like this, the width of the metal, the spacing from metal to metal, we have to maintain. And if we draw a via, that via should be appropriately connected as per the enclosure. That means the connectivity will establish perfectly from metal 2 to metal 3. If you are not putting these pillars, okay, properly, will the second floor and third floor will stand or it will fall down? It is not working. It is not going to work. Yeah, Sharon Reddy, hysteresis losses and copper losses are calculated electrical properties or electrical characteristics. So each and every metal has different kind of metal properties. So if we see higher metal layers, those higher metal layers are made up of copper, gold, aluminum, silver. Okay. If we are going for the lower metal layers, they are manufactured of bronze or they are manufactured of some other low quality metals. Yeah, aluminum. So on the top metal layers, so most of the costly chips, alloys also. Yeah, most of the costly chips like Intel Xeon, AMD, EPYC7451, these all chips are made out of connectivity, good connectors, gold. So only the chip cost is very high. So this is how the VLSI engineers are very costly and they are paid very high. So the electrical characteristics like max current density is present. So the current density, as I have told you, each and every metal has some width and length. So it has some RC properties or RLC properties. Resistance, capacitance, and inductance. So based on that, it will have current density. So to maintain that current density electrical characteristics, we need to draw the layout very perfectly. And whereas in case of physical design, the tool takes care of it based on the technological information. Whereas in case of analog layout design engineer, he has to do the manual layout. Okay, the tool will guide the layout engineer if there is any violation while he is drawing the layout. Clear so far, everyone? Understood? Technology file information. What technology file consists of? .tf file. Correct, yes. Sharon Reddy, yes. Thank you, buddies. Yes, Sharon. Next is TLUP, max TLUP, minimum TLUP. Okay, I have said you each and every each and every standard cell has maximum values and minimum values in the library. So, as a human beings, okay, if something goes wrong in our house or in our surroundings, we will get some angry, we will get some kind of aggression, and we can be also neutral if there is nothing, and we can go into sad part also. So in like that, the standard cells has minimum characteristics, maximum characteristics, and moderate characteristics. That is how they are going to define using RC parasites of metal layers per unit length. Okay. Next is these RC parasitics are used for calculating net delays. Okay. Tau is equal to RC. That is nothing but the delay. Understood everyone? The formula tau is equal to RC. How we are going to calculate the net delay? Using the resistance and capacitance of the wire or the routing net. We can get TLU plus files from ITF file. ITF file is nothing but interconnect technology file format. So whatever the RC values, whatever the TLU plus file values, those are designed from ITF files. That ITF files are nothing but technology files. For loading TLU plus files, we have to load two files, that is max TLU plus files and minimum TLU plus files, which has maximum timing delays, maximum area delays, maximum power delays. And minimum is nothing but it has everything minimum. Next is map file. Map file will have layer and vias information. Layers is nothing but poly, oxide, metal 1, metal 2, metal 3, metal 4, metal 5, and up to 9 metal layers if you are using 9 metal layer design. And about via information, metal 7 to metal 8 via, 8 via, metal 5 to metal 4 via. If you want to draw a metal via from 4 to 3, okay, 4 to 7, example, we have to draw metal via from 4 to 5, 5 to 6, 6 to 7. Okay, this is how the information of map file has. Clear? Is everyone able to understand what is the input file of TLU plus files for Synapse system? Someone please reply whether you understood or not. If you have any question, please post it on the chat window. Jaydeep, yes. Tarak, explain again, sir. Tarak, you are not attending them. So the TLU plus files, we will be giving it to Synapse systems. This TLU plus files has resistance and capacitance of each and every metal layer per unit length. So if we have unit length of metal piece, okay, for that metal piece, we will have a calculated value of calculated value of resistance and capacitance. Based on that resistance and capacitance for metal 1, metal 2, metal 3, metal 4, and top level layer metal 9. So we are going to calculate RC values and we are going to put in a table. So example actually. Okay. So this is my table. So this is metal. This is R. This is C. This is metal 1. My R value is 100 ohms and C value is 200 picofarad. This is ohm and this is picofarad. And the information is metal one. And the unit length is nothing but this much size of unit length. So this much size of unit length, we are going to have RC values in a table form, like 100 and 200. 100 into 200, what will be the value? That much delay we will have in the PLU plus max file and minimum file. This is how we are going to calculate the net delays. So if my net length is this much, okay, this means almost all 3.2 units. Example, okay, 3.2 units into per unit it is 100 into 200. What will be the value? That much value will be calculated as RC values for a net delay. Okay, Tarak. Next is map file. Map file is will have the layer information, via information. Layer information means metal one. Metal one is made up of copper. Metal two is made up of aluminum. Metal three is made up of silver. Metal four is made up of bronze. Metal five is made up of some other metal like brass. Metal six is made up of gold. So, like that, this layer information will be. And to draw the via, okay, this is my metal one. This is my metal two. So I need to draw a via here. This is via 1, 2. So it has to use a alloy of copper and aluminum. So that is how the fab people will design. This information we will have in map file or .tf. Okay, clear everyone? So far? Clear participants? Ishwar, Tarak. Pravalika. Thank you. Smita Lata. Gangotri. So after a long time. Pavan. Chaitanya. Nagendra. Gauri Priya. Anji. Monish. Nagesh. Rohit, if all metal layers of same type, okay, we can use, but most of the times they will not use. Why? Because each and every metal has its own different properties. That is about metal science. So what metal has to be used, what properties has to be calculated, that foundry team will take care. Okay, we will not use all the same metal layers of similar metal type. Rohit, okay? Akila, Daya Shankar. Anyone else who are attending my class? The new candidates. Jananaid. The new candidates. Chakrapani. Okay, we'll proceed further. Next. These all are input files for our floor plan. So next is library exchange format. Library exchange format, it contains the physical information of standard cells, macros, pads. Okay, so macro is nothing but a already predefined design. We want to instantiate the design in our floor plan. Okay, so for that purpose, we are going to use macros. Or if there are some standard cells like NAND gate, NAR gate, XOR gate. Okay, and next is IO pads. This all information will be available in left file. And left files also has location of coordinates where we are placing in our core area. So this will have coordinates. I'll show you when I am doing the design on the tool. Pin layer information. So we have some pins. So each D pin, clock pin, and all those pins. This pin layer information also we'll have in .left file. And direction of the pins, whether it is input pin, output pin, or in-out pin. And the pin configuration like signal pin, power pin, ground pin. Signal pin will have less density, power pin will have high density, ground pin will have high density and width and height of the pin and cell. This all information will be in the left file. And whatever the size of the standard cell, this size, height, width, all these information, symmetry of the cell also will be in the .left file. Clear? Library exchange format or layout exchange format. Can I move to the next slide? Tarak, yes, sir. Only Tarak is listening. Okay. Next is .lib file. .lib file will have timing information of the standard cells and macros, functionality information of the standard cells, whether it has work as NAND gate, NAR gate, and or inverter or anything, whatever the logic is. Timing, DRV like max transition, max capacitance. .lib file has this information. So maximum transition and maximum capacitance. In timing information lookup table is used for output transition, cell delays, setup, and hold time analysis. Cell delay is a function of input transition and output load. So if we are taking, okay, any cell like standard cell or any gate, for example, okay, so the cell delay is calculated based on once the clock is triggered, the data transfer time taken, okay, from the data pin to reach the Q output pin with a clock amount of time. That is called cell delay. It is calculated based on the input transition and the output load connected. The output load connected is just a pin. If you are connecting any logic, then this will be the load. Okay. It is also a wire load model. Wire load model is nothing but WLM. Wire load model is a Excel sheet or CSV file which will have resistance, capacitance, values for each and every net term. It contains power information of the standard cells. Whatever the standard cell is there. Based on the input transition, output load, cell delay, and everything, the power consumed by each and every standard cell is also available in .lib file. Clear? So far, everyone? Any questions? Proceed further. Design rule valuation. There. Okay. Nagendra, explain one more time. So, if you are considering the .lib file as an input for floor plan, okay, what .lib file has the information about timing information of standard cells and macro. So, if you are considering the standard cells, okay, this standard cell has DFF functionality. So, this information is available in .lib file. And the standard cells functionality, whatever the logic it has, that functionality is also written in .lib file. And the maximum transition and maximum capacitance value, RC values, like which are tabulated like a Excel file or CSV file using table lookup files. That table lookup files are called as WLM, wire load model. And the standard cells information about power. Power information is also available in .lib. Clear, Nagendra? Yes, sir. So this is how the delay tables looks like. So if we have a cell, this is one cell, this is one standard cell, which is having the pin information of Y and the timing information, rising relays, okay, which are having a variable values based on the input transition, output load, the delay RC values. Here, input net transition and output capacitance. Input net transition is nothing but it is taking the time to transact the value from input to output. And the output load. What is the output load? This is my output load. And what is the wire load model? This capacitance. And this net length. All these are wire load models. So cell delay is a function of input transition and output net capacitance. Clear? Delay table. How the delay table looks like? Is everyone following? Yes or no? If yes, we will proceed further. If no, if you have any questions, please let me know. Okay. Thank you. As we have seen, the gate level netlist, the gate level netlist has standard cells and its gate numbers and standard cell gate information. And if at all, if we have any macros, okay. Tarak, you are diverted and you have come back. Please try to avoid these situations in the next class session. Okay. Blackbucks team will take necessary action and they will cancel your registration for you. There are possibilities. Okay. Rohit, Tarak, and all these people try to avoid these challenges chatting in Teams or meeting. Okay. So they will try to cancel your registration and they will remove from this internship without any fair explanation. Okay. We are not answerable to anyone directly. Strictly, I'm saying. So everything is recorded and everything is documented. The session completely. If any mischievous thing happen, they will take necessary action on each and every candidate. So only they have made a mandatory login of Gmail account. Okay. Hope better. Someone voice is not audible. Why? Is my audio clear? Yes. So try to avoid these kind of situations from your side itself, unless until we warn you. If we are warning, we will take action directly. Okay. So not myself, Blackbucks team will do that. They'll nothing they'll do, they'll not make you to attend the classes anymore. That's it. So the another input file for floor plan is gate level netlist. Gate level netlist will have .v extension, which will have the logical information of standard cells after doing translation, mapping, and optimization of our Verilog code. If we have any macros, that macros information also will be available in our gate level netlist. It contains list of nets connecting standard cells and macros. So all these wires, the wire information, this is called nets. So that is connectivity. Each cell has its own instance, cell name, and library reference name. So this is the cell name and library reference name and to G1. Okay. And this is coming from standard cell library. Clear? Gate level netlist. Yes. Thank you. Next is SDC, standard design constraints. Standard design constraints are of two types. One is user defined design constraints, and next is design related constraints. These constraints are mainly used to meet the timing requirements of the design, like clock definition, clock uncertainty, setting up input delay, setting up output delay, driving cell, setting load and output ports. Like timing exceptions, multi-cycle path, false path, half-cycle path, disable timing arcs, case analysis. So when the static time analysis topic comes, I'll be teaching you about all these detailed concepts about clock uncertainty. Clock uncertainty means clock definition, you know. We'll write in the Verilog clock equal to negation of clock for every 10 units of time. When the duty cycle of the clock is 20 units, the full cycle. This is 20. The clock uncertainty means the data came from before the rise edge or after the rise edge. The clock uncertainty is this one. This window is called clock uncertainty. We have to board our flight at 9 p.m. But we will be reaching airport either 8:50 or 8:40. The flight can come after 9:10 also sometimes. But the boarding time is 9. So the window is called uncertainty. Here, next is input delay. So we want to set some input delay to our transition. So this is 0 input delay. Give me a minute. I'll fetch some water. My throat is going dry. Tarak, you are the good listener of the class. You are directly straightforward asking for attendance link. It's not fair, Tarak. Try to learn concept as much as time you spend in the class. Okay. Then why you are asking attendance link? They will send in time. Our class session is from 7 to 9. Okay. Once they send the attendance link, you can try to give your attendance. Okay. So coming to the delays. So if this is ideal clock, I want to set some input delay. So this is input delay. I'm introducing it mandatorily. And next is I want to capture the output on this clock edge, but I am trying to insert the output delay. This is output delay. Next is driving cell. So I have a logic. I am connecting another logic. Then this is called driving cell. If I am connecting at the output, that is load cell. See, what is the use of input delay, output delay, all these delays? So in some cases, my data will be generated from one logic to another logic, and it is an interconnect of all the different logics. But the logic one is taking 5 nanoseconds of time to compute, and to send the data to the next logic, it is taking 10 nanoseconds. But the clock is 10. But the duty cycle is 20. But where is my 5 nanoseconds losing? I have to adjust in input delay or output delay. The computation time of logic is 5 and the sending time is 10. So it is 15. But my duty cycle is 20. I have to adjust it for 5. Then I have to set up input delay or output delay. I have to set up input delay. Clear, Hemant? Okay, sir. Thank you. Next is timing assumptions. So timing assumptions, just for terminology, we'll understand it as multi-cycle path, false path, half-cycle path, disabled timing arcs, and case analysis. These all are the naming wise timing exceptions for today's class. In when we are teaching about static timing analysis, I'll explain you about timing exceptions. Clear so far, everyone? You are attending my session about floor plan, input files for floor plan. Yes, Lata. Thank you. See, next is what is block level design? Siddheshwar, thank you. What is block level design? Large chip with millions of cells is divided into a small subsystem called as blocks. So I have a big chip and each chip has some blocks. So all these blocks combined together form a big chip. Dividing a full chip into blocks is called partitioning. The concept of partitioning is we are dividing a big full chip into small sub blocks. Then it is called partitioning. So there are different kinds of orientations like abutated, non-abutated, and mixed. So abutated means from the block to block there is no spacing. And in non-abutated they are aligned in a different orientation. and different dimensions. And in mixed, combining unmuted and non-unmuted, it is called as mixed. Clear? This is how the block level chip design or full chip level design is done. So if you are designing one block, and if you are designing block 2, block 3, block 4, block 5, and block 6, and the top level engineer, your manager, who will align all these blocks together to form a full chip. Clear so far, everyone? Next is floor plan. Floor plan design. So it's a process of creating an area for macros and standard cells to be placed in efficient way. Okay. So this is definition wise. Floor plan design to it is a process of creating an area. We are creating some area. Okay. Creating an area for macros and for standard cells. Macro 1, macro 2, and some standard cells. These standard cells are placed in some orientation in a efficient way. See how neat they are looking. So this is called floor plan. Floor planning steps decide core width and height of the die size estimation. We are going to estimate core size, die size estimation, and placement of IO pins, IO pads, input output connections of ports. Next is creating voltage areas. So we have some high voltage areas in our design. So we'll be creating high voltage design areas. Next is placing macros. Adding physical only cells. Physical only cells means they are like black boxes where we need to paste blindly in our design. Their logic is written, but we don't understand what is their logic. We directly have their connectivity. We have to directly connect it. Next is power planning. Based on the available spaces, we will be doing power planning, VDD and ground connections. This is what floor planning is. The following steps we will be doing in the floor plan. We will decide die area, core area, height and width of the chip size. Next is we will place IO pads and IO pads, IO ports, creating the high voltage ranges, placement of macros, adding physical only cells. Next is power planning. Power planning is nothing but we will write the power lines, VDD and ground. Hope so far is clear. Everyone. Hemant, the question is clear. Okay. So at the synthesis stage, we got count of standard cells. So standard cells has some area. Okay. Based on this count, we'll multiply with the area of each standard cell. Then we'll get some estimated area of standard cells. If we have macros, the macro area is given in the data sheet. The standard cell area we have calculated from simple system. So leaving the 60 to 70, 50 to 60% maximum. Of core utilization, we are going to place the standard cells and macros in the core area. Clear, Hemant? So far? This is all estimation. Based on the estimation, we are going to place the macros and standard cells. And remaining 30 to 40%, we are going to use for routing clock trees, routing signal nets, and remaining kind of activities like ECOs in physical design. Hemant, did I answer your question appropriately? Yes, sir. You are happy, right? Thank you. So this is how we are going to do the floor plan. So this is this is 4. And these all are IO pads. And this is IO clearance. That is nothing but 4 to die area. And the inside these horizontal lines are called as fallow pins. And the blue color things are standard cells. They are fit to height and width of standard lines. They are of equal size. And these all are macros. So this is how we decided the area by floor plan. This is some 60%. And when we do clock tree synthesis, routing, these all cells will be realigned based on our floor plan. At that time, maximum 90% of utilization comes into picture. This is how we decide the core area, the area. There is some mathematics formulas that also will be taught. Okay. Clear so far, everyone? Everyone is able to understand? Any questions? Please let me know. We'll end up the session for today here. Clear, sir. Tarak, thank you. Everyone, thank you for your. Is it mandatory to write a daily test? Gauripriya, you can talk to Blackbucks team. I am not the correct person to answer. If you are writing the assessments, if you are writing the daily tests, okay, this is testing your knowledge, whatever you are understanding. See, simply, if we watch some serial in TV, okay, for the first 2 minutes or 3 minutes, what they will do? They will do the recap of previous episode. That also we will watch in TV. As this is our life, we are learning the some concept or some situations. Okay, if we attend a test, okay, based on the test, we are going to test ourselves how much we are understanding the subject. Initially, you may fail, initially, you may pass. Doesn't worry about that. Give the test and understand your capabilities about the subject. Right? Gauripriya, please try to do this. This is a regular practice. Even I do for my day-to-day life. Before joining the class, I do the activity. I walk through my slides. Whatever I have prepared, I have to teach. Just for 10 to 15 minutes, I'll watch all the slides. The overview of class today is the output of synthesis files we are importing to the floor plan. So the important floor plan import files are SDC. Okay. UPF, scanf, def files, lib files, and Verilog netlist. These all files are the input files for floor plan. And detailed description, the inside of each and every file, what information it has, and what is floor plan, and how we are going to design the floor plan for a block level design of a chip, how we are going to assign IOs, how we are going to place the standard cells, how we are going to design the core area, die area, and standard cell rows and everything. This is about floor plan. And next slide is related to the mathematical calculations, how we are going to decide the core area or die area. Okay, that's all for today. Good night, team. Thank you for attending the session. Bye.